to figure out what the null and alternative hypothesis would be for each of these tests. So it helps to keep track of the original claim. And this one, the original claim is the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. Now, the original claim, you could set it up this way. P sub 55 is greater than P sub 25. If you want to use, say, P sub 1 and P sub 2, then I wanted you to write out what P sub 1 is and what P sub 2 is on the test. So P sub 1, the proportion of people greater than 55, who dream in black and white. Now you only have to do this for the hypothesis test where there's two possible parameters. That is, you have, not two possible parameters, but there are two parameters because you've got, one population and another one, black and white. I think it's just as easy just to subscript it with something relevant to the problem. P sub new, P sub old, P sub black, P sub white, whatever it happens to be, just subscript it. But this kind of original claim has to go in which hypothesis, your null or alternative? Alternative. Has to go in the alternative. P sub 55 is greater than P sub 25. That means that P sub 55, you could do one of two things. You could put less than or equal to less than or equal to P sub 25 or equal to. My stat lab works with the equal to. I'll accept less than or equal to. Either one is fine. So there's the first one. Thoughts or comments on that one? Looking okay with that? Yes? Great question. There's no dependent and independent with population proportions. The dependent and independent only happens when you have two population means. Then you have to decide dependent or independent. If it's one population test, then you don't have to worry about that. If it's population proportion, again, you don't have to worry about that. All right, good question. Let's move on to the next one. Systolic blood pressure levels above 120 are considered to be high for 300 such measurements. The mean is 122.6, and standard deviation is this. Tested claim that the sample come from a population with a mean greater than 120. Which parameter am I testing? U. So it's going to be mu is greater than 120. Which hypothesis does that have to be part of? Has to be part of the alternative. Mu is greater than 120. So here you could either write mu equals 120 or mu is less than or equal to 120. Doesn't matter to me which. It's kind of up to you. Let's get rid of this. There we go. Nice. Now, my hope is that, if you can start out the right way, then you can finish up the right way. So suppose you actually had to do the whole test all the way through. So you'd be using StatDisk or some other statistical package. You're going to go to analysis, hypothesis testing. Well, what are your choices? Well, it has to be a mean of some sort. You've got three things for a mean, but only one of them is for one sample. Then you adjust the alternative hypothesis. So we want a greater than significance level. Let's assume it's 5%. Claimed mean. Where does the claimed mean come from? Where did I get the 120? Yeah, that's going to be in your null hypothesis right here. So 120's the claimed mean, standard deviation. We'll never know the population standard deviation. Sample size was what, 300? Mm-hmm. Sample mean was 122.96. Sample standard deviation was 15.86. And bam. What information do I want here that's going to help me decide if I reject or fail to reject? P-value. P-value. What's that little saying that I've been using to help you remember whether or not to reject H naught or fail to reject H naught?
H naught is low, it must go.
If P is low, H naught must go. So if P is less than alpha, you're going to reject H naught. So is P less than alpha in this case?
Yes.
Absolutely. Reject H naught. Now they give you a confidence interval. Be careful about this confidence interval. A lot of times there's follow-up questions about a confidence interval. You're probably going to be asked something and they might want a 95% confidence interval. But if you look, they give you a 90% confidence interval. So that's not quite in sync with what our alpha is. You can get a 95% confidence interval by just redoing this. Go over here to, mean one sample, get your confidence interval from there. Or if you really want to be sneaky, you can do 0.025, and that should give you your 95% confidence interval. All right, let's continue. Data set 3, the IQ scores for subject with 2 sets of blood lead levels, low and high. Below the summary statistics, test to claim that lead exposure has no effect on IQ scores. So let's think about that for a second. So the first thing we need to decide is how many populations are we testing? 1 or 2? 2. So we're going to branch down here. What parameter do you think we'll be testing? Yeah, for 2 populations, just because of the way the course is lined up this semester, we only have 2 populations test. 1 for proportions and 1 for means. Actually, we got 3, I guess, because there's 2 here. Is this going to be a dependent or independent sample test?
Dependent.
Dependent? Why?
Because one doesn't affect the other.
If one doesn't affect the other, then they are...
Oh, that's independent.
Independent, yes. These are going to be independent because somebody's IQ with a high blood lead level is going to be independent of somebody else, assumingly unrelated, with a low blood lead level. So, yeah, that's going to be a deep independent case. So let's do that. I would set it up like this. Let's see, original claim, OC. We've got mu sub low and mu sub high. But if the blood lead level has no effect on IQ, how should these compare? Equals. If having more lead in your bloodstream has no effect, then these would be equal. So that's going to be part of our null hypothesis. And our alternative hypothesis is mu sub low and mu sub high. What should I put in HA?
Not equals.
Not equals. Beautiful. So again, if you had to do the hypothesis test, all the way through, you pick analysis, hypothesis testing. This time you pick mean 2 independent samples. Bless you. This one's going to get tricky for a few of you. A simple random sample of birth weights of girls has a standard deviation of 829. Use a 1% significance level to test a claim that girls have the same standard deviation of birth weights as boys, which is 660.2 grams. The tricky part is that I've given you a couple things. So my first question to you is, how many samples are we dealing with? Just a 1 or 2 sample? Well, there's a couple ways you can draw an inference. One is that the problem talks about a simple random sample of 30 girls and a standard deviation. So that's your 1 sample. There's no second sample. The other thing that you can kind of fall back on is that we haven't learned this part yet. We haven't learned sigma 1 and sigma 2. That's section 9.4. So we're not there yet. That won't be on this test. So there's a couple ways you can arrive at the correct conclusion. Hopefully you realize that, okay, there's just 1 sample here. That's tough because I do talk about this other one. I'm like, hey, Boys have a standard deviation of 660.2. But that number is not coming from a sample. It's not sample data. It's just coming out of the ether someplace. So we'll just use that. That's our original claim. So for our original claim is that sigma equals 660.2. Matilda, where is that going to go? HO or HA?
HO.
HO. Notice that in all our HOs, you have the possibility of quality, and in our hypothesis in general, you're testing parameters. Please do not put S, P hat, or X bar. Those don't belong here. Those are some easy points to get wrong. Please don't do that. Awesome. Let's move on to problem number 5. The heights of mothers are given in data set 10, heights of mothers and daughters. Test to claim that there's no difference between heights of mothers and heights of daughters. All right, well, what parameter are we testing? Because I didn't really say. You've got a choice of mu, sigma, and P. You've also got to decide one population or two populations. What do you think? Let's do the one population versus two populations first. How many populations do you think we're working with here? 2, because you got mothers and daughters. All right, so that brings us down here. Which of these parameters are we testing? Proportion, sigma, or mu? Mu. Last but not least, for something like this, you got to decide dependent or independent.
Independent.
We've got a little disagreement here. I heard dependent and independent. Which one's right? Dependent. There's going to be a relationship between the heights of a mom and her daughter. They're not going to be independent. You're not going to have a mom, which is, maybe 5 foot and a whisper, having a 6 foot daughter. All right. That's probably not going to happen. So they are going to be dependent. So that should be part of your choice here. Let's see. Let's write that one down. Now, as far as the original claim, there is no difference. What should I write here then?
Equals.
Yeah, mu sub mom equals mu sub daughter. That's your original claim. That's going to fall onto an HO and an HA this way. Mu sub mom equals mu sub D, mu sub mom not equal to mu sub D. Nice. Let's keep going. Comments or thoughts on number 5 there? So, let's see. Number 6. This is a problem that I didn't get to do in class the other day, so I threw it on your review here. I think I mentioned in class that what struck me about this study is that it took place right here in Michigan. Again, you got to be careful about the number of populations you're dealing with here. So Black Americans represent 14.1% of the population in Michigan as of 2020. As of November 2020, 35% of COVID deaths were among this group. Tests to claim that the proportion of mortality amongst Black individuals was greater than the percentage in the population of Michigan. So I actually cited the article there for you if you want to follow up with that. Let's think about our original claim. How many populations are we dealing with here?
1.
2 or 1?
1.
It's just 1. All right. So the people in Michigan, you're either African American or not, but it's just 1 population. What parameter are we dealing with?
P.
P. All right. So the other part that's sticky on this one is right here. Black individuals, their percentage was greater than that of the population in Michigan. So that's gonna be P is greater than what? You've got two choices, two numbers that are there. It's either the 35% or the 14.1%. Which one of them is right?
14.1.
Yeah, the 14.1, because that's their percentage in the population of Michigan. So 0.141. Okay. So that actually has to be part of the alternative hypothesis. It's not a mu, it's P. My bad. You can write this as a decimal or a percentage. If you write 14.1%, that's fine. I'm just going to write equal to just for a little bit of variety here, but you can write less than or equal to. That's fine. I accept that. Trials and experiment with polygraph yield 98 results that include 24 cases of wrong results and 75 cases of correct results. There's a subtle little thing here that is easy to overlook. What's 24 plus 74? Come on, somebody help me out. 24 plus 74. 98. That's it. There's just one sample here. It's just telling you that some of these are wrong, some of them are right, but there's just one sample here. And that one sample has to pertain to a population proportion. The claim is that, so original claim is that these are right 80% of the time, P equals 0.80. That's your original claim. That's going to go in H naught. HA, of course, is going to be that they're not equal to each other. Hey. Okay, let's keep going. So flipping things over. So on the back side, the mean resting pulse rate of 32 instructors has a mean of 57 and a standard deviation of 12. We want to test this claim, and we get a resulting p-value of 0.083. I think I gave you the significance level. Significance level was 0.05. What's that say about our null hypothesis? Are you going to reject H naught or fail to reject H naught?
Fail to reject.
Fail to reject. All right, so fail to reject H naught. And then your justification is that P is greater than alpha. That's it. If the p-value is low, H naught must go. Well, it's not low, it's high. It's higher than alpha, and that's kind of your gold standard there.
Is that all we have to put on like the test if that was to pop up? Just P is greater than
Yeah,
alpha?
yeah, that's good enough. Yeah.
So we don't have
I
to do this?
I could make it,
Thing?
what's that?
We don't have to choose between.
Well,
Yeah.
now, let's keep in mind a difference here. All I'm asking you to do right now in this practice is figure out where to start. Now, you could end up doing the whole thing depending on the problem, but if you can't start in the right place, how are you gonna get the rest of it right? So that's why I wanna practice this right now. Now, if you wanted to actually do this one, let's go ahead and see what it would look like to do this one. So let's see, the couple things that I would note down for us. We have n equals 32, x bar equals 57, and s equals 12. All right, so those are the things I want to note for myself. We'll go to StatDisk. You know what, we should probably set up our original claim, our null and alternative hypothesis. Our original claim, testing the original claim, the pulse rates. Well, we don't even have an original claim here, so let me make one up. Is that mu equals 60. And then H naught, mu equals 60. Mu is not equal to 60. Let's see if this is a big enough sample size to conclude that there's a difference. So if you got this far, then what I'm hoping is that you can go to StatDisk and say, all right, I know it's going to be a hypothesis test. Analysis has got pretty much everything you want. You go to hypothesis testing. Which one of these choices do I want?
Mean one sample.
Mean one sample. It has to be a mean. You've only got one sample, so that makes a clear choice. We're going to set up your alternative hypothesis. You've got 3 choices. Let me let you look back here. That's our HA. Let's look back. Do I want 1, 2, or 3 for my alternative hypothesis? 1, good. So we'll leave that as 1. We'll do this at the 5% significance level. The claimed mean was 60. That comes from your null hypothesis. N was 32. The sample mean was 57. The sample standard deviation was 12. Bam. What information do I need here? P-value. So if we're kind of following along with how we laid this out during the week when we're covering these kinds of things, step 1 was state your null and alternative hypothesis. Step 2 was decide on alpha. Step 3, we input our data. Step 4, our p-value is 0.16. What should I do for step 5? Somebody gave it to me. Fail to reject H naught. P is greater than alpha. And last but not least, it's state your conclusion in words. So that's the 6th step. On the exam, I will give you a copy of the handout for stating your conclusion in words. That's going to look like this. So our original claim in this one is that mu is equal to 60. Okay, great. So let's take a look here. Mu is equal to 60. Does your original claim contain the condition of equality?
Yes.
Yes. Do you reject H naught?
No.
No. So there's not enough evidence to warrant rejection of the claim that the mean pulse rate of hams is 60. So there.
Where do you get 60 from?
I just threw that in because I mean this problem wasn't originally designed to be done out all the way, so I just made that up on the spot. It's actually what I did when I came up with this number originally. I think, or so I think I did it one side. I said it was less than 60, or something less than or greater than. I can't remember which. All right, so back to this part. There is not sufficient evidence to reject the claim that the mean pulse rate is equal to 60. Notice I didn't use any symbols. I didn't use H naught, HA, I didn't use mu, etc. I want it in words, and I also related it back to the problem. Talked about the pulse rate, and I mentioned that we were working with the mean. So that's got pretty much everything I would want in terms of a conclusion. But the reason we're practicing things this way, where we're setting up the null and alternative hypothesis is because, if you can't decide where to start, where you're going to be in trouble. And on the test, you're not going to be doing 6 or 8 or 10 of these in a row from section 9.2. You're going to get a random selection of these things, and you're going to have to recognize, oh, well, this is 2 populations dependent. This is 1 population proportion, that kind of thing. All right, let's keep going. Problem number 9 represents a different way I can give you a problem so that you don't actually have to enter in all the data into StatDisk. You can just work it from looking at this. So the question is, if you're given a 95% confidence interval for the population mean, which is this, how does this confidence interval compare to your decision up above? In other words, are you going to reject H0 or fail to reject H0 based on this confidence interval? And of course, why? But I may or may not ask you the why part depending on how I give you this problem. But does this confidence interval suggest that you should reject H0 or fail to reject H0?
Fails reject.
Good, fail to reject. If you're asked why, what would you say? Yeah, 57 falls in the confidence interval. So if the confidence interval contains this, why would you reject it? That's in your confidence interval, keep it. Cool. All right, so 9, fail to reject H0. 57 is in the confidence interval. All right, let's move on to 10. Researchers conduct a study to determine whether magnets are effective in treating back pain. Pain was measured using the visual analog scale, and the results are shown below. Higher scores correspond to greater pain levels. Assume that 2 samples are independent, simple random samples selected from normally distributed populations. Test a claim that magnets have no effect on pain levels. How many populations are we working with?
2.
I got a couple votes for 2. Is that unanimous or not sure?
2.
2, all right, two populations. Now this one's not under consideration. Are we dealing with population proportions or population means?
Proportion.
Proportions. Dependent or independent?
Independent.
Independent, yeah, I think it said it in the problem, right?
Yeah.
Independent, simple, random samples. I mean, that's pretty clear there. So, let's see. Test a claim that the magnets have no effect on the sham or have no effect on the pain levels. So, if that's true, our original claim is that mu sub magnets and mu sub sham treatment, which is like a placebo, how would those 2 means compare to each other? If the use of magnets has no effect compared to not getting a magnet. Equals. So again, you could write either mu sub magnets, mu sub sham, or you could use mu sub 1, mu sub 2. But if you're going to do mu sub 1 and mu sub 2, please write out mu sub 1 equals the use of magnets, mu sub 2 equals sham, that kind of thing. Mu sub magnets equals mu sub sham. Mu sub magnets not equal to mu sub sham.
I thought it was proportion.
What about this suggests it would be a proportion? Okay. Now, the last thing you got to do here is make sure you put that this is the independent case. Now, something kind of weird happened when I was printing these things out. The auto numbering got off. But the probability of a type 1 error, you had to be listening pretty closely when I mentioned this in class, but the probability of a type 1 error is just alpha. Alpha, your significance level. So it's a number that we're familiar with, we've used all along. I just want you to keep in mind that that's what it is. It's your chance of a type 1 error. Now, how big or small you make this is going to depend on the consequences. What is a type 1 error? What does it mean in terms of this problem? Does that mean you're going to get something wrong when it's really a bad case to get it wrong? Well, you know, if that's the case, then you want to make alpha really, really small. Of course, you might, you know, not ever reject H0 if you make it too small, but, you know, that's a decision you're going to have to make. So the follow-up question to that is, well, what is a type 1 error? What am I looking for? So let me remind you, a type 1 error, that's rejecting H0 when it's true. So rejecting a true H0. Or rejecting H0 when it is true. How about a type 2 error? Well, in a type 2 error, that's failing to reject H0 even though it's false. So failing to reject H0 when it is false. Okay, what would that look like in the case for problem number 13? I guess in problem number 13, what you got to do first is this. You got to decide what the claim is. The claim is that the mean weight of border collies, which are so cute, energetic, and adorable, mean weight is 42 pounds. So that would be mu equals 42. That's obviously going to be part of your null hypothesis because it contains the possibility of equality. I'll be happy to give you these things right here on the exam. What I want from you in return is what a type 1 and type 2 error is in words. I don't want a definition. If you give me a definition, let me thank you in advance. You're going to make it really easy for me to grade. All right? I don't want a definition. I'm giving you the definition. You tell me what it means in words. So if you haven't already done so, try and write down what a type 1 and type 2 error is. I'm looking for two things. I'm looking for what's true about H0 and how your decision compared to that. So why did you make an error? So I'm looking for, tell me what's true about H0 or tell me what's not true about H0. There's a variety of ways to word this. These aren't the funnest problems for me to grade. I actually have to, I don't know how to put this politely, think.
But you said what's true about H9 and what else?
And what was the decision in comparison to that? If you're watching this at home, you can fast forward till that pause is removed. Does anyone want to give the type 1 error a chance? See what you got, hear my critique of it. Kumar, I think I saw you're up first.
Although the mean weight of border collies is 42 pounds, the data rejects the claim.
Sure. Although the mean weight of border collies is 42 pounds, so that's basically saying that H naught is true, the data reject that claim. So you're telling me what was true, you're telling me how your decision compared to what was true. Anyone else want to try? Matilda, I think you had your hand up as well.
For rejecting claim that the mean weight of border collies is 42 pounds, when in fact the mean weight is 42.
Perfect. Reject the claim that the mean weight of border collies is 42 pounds, when in fact the mean weight of border collies is 42 pounds. Again, perfect. Here's what I wrote. While it's true that border collies have a mean weight of 42 pounds, the data reject that claim. You know, again, you're getting at the same thing. You're telling me what's true about, or telling me what's going on with H naught, and then you tell me what the decision was in comparison to that. How about type 2 errors? Anyone get that far? Hudson?
I said the claim that the mean weight of border collies is 42 pounds is false, but the data failed to reject that claim.
Beautiful, beautiful. That's close to what I have too. Border collies do not have a mean weight of 42 pounds, but the data fail to reject that claim. I've got another version of it as well. Although it's true border collies have a mean weight different than 42 pounds, the data fail to support that claim. So that's, you know, saying again the same kind of thing. Now there's one more thing you want to keep in mind for the exam, which is going to cover sections, I think like 7.1 to 9.3. Is that right? Everything in there that we covered. And that is, you're going to be asked to interpret confidence intervals. So here's a confidence interval that we dealt with. 95% confidence interval for the above data is between 52.7 and 61.3. So what I would say about that is that we can be 95% confident that the true mean pulse rate is between 52.7 and 61.3. One thing that I really like here in these kinds of statements, actually a couple things, but one of them is that you talk about the parameter, call it the true mean, the true proportion, true standard deviation, whatever the case may be. But this is a way for people who don't have, or who have a little bit more understanding of statistics, to realize that you're talking about the population parameter, because that's the true mean. We don't know that, which is why we're creating a confidence interval. We're saying, yeah, well, it's in here someplace. We just don't know where, because we don't have all the data. So I like that. Tell me the confidence rate and describe what that is. It's the pulse rate, you know, and it's between these two values. So hopefully some easy stuff there for you, but do kind of format it similar to this. Doesn't have to be exactly like this. George?
So for proportion, you only need it with state as proportion?
Well, you'd have something for proportion if it talks about percentages or proportion, all right? So if they say 80% of voters feel one way, then obviously that's going to be a proportion. They don't have to say that 95 times out of 120 voters voted this way or something like that. That would also be a proportion, but yeah, proportion can be stated in a couple different ways there. Anything else on this one? Yes, please, Kata.
You said percentage of typically proportion, I remember said that we used the mean.
So let me go back to problem number 7 there. No, you would not be using mean here. This would be a percentage problem, so you'd use a proportion on that one. So the hypothesis test in that one was the proportion was equal to 80% or not equal to 80%. Okay, have a good one. See ya.